could hear it perfectly. Welcome. My name is Daryl Budd. I'm the Dean of the College of Mines and Earth Sciences, and I have the honor of introducing our speaker this evening. But before I do, let me just say a few words about this series. How many have been to many of these? Is this quite a few? So we have some loyal customers. That's fantastic. This is the 50th anniversary of this series. Did anybody come to the first one? No? There's probably a couple faculty in our department that did, but one? Really? Who was? I don't recall. I'm new around here, actually. But believe it or not, there have been over 450 scientists that have presented at this symposium, which is pretty amazing. The list includes National Academy members, members of the Royal Society London, Guggenheim Fellows, MacArthur Fellows, and Nobel laureates. So it's a very distinguished series of presenters, and tonight's no exception. If you're interested, a lot of the recent lectures are also on the YouTube site that you can access through the College of Science. So you might want to take a look at that, and you can watch tonight's presentation again if you want to. This is the first of 6 lectures. We're going to have 6 lectures this year, and we have approximately one a month with 2 exceptions. We don't have one in October, and we don't have one in December. So there's one in November, January, February, March, and April coming up. So please join us for those and bring some friends with you also. The topics are going to range from climate change and ecosystems to energy, time travel, archaeology, and nuclear non-proliferation. So we've got a really interesting group of talks this year. With that, I'd like to introduce our speaker this evening. Many of you know her already, I know. In fact, Dr. Pooh, who's in the front row, was her first graduate student, so she knows her well. Probably has a little bit of PTSD from it, I'm guessing, as all graduate students do with their advisors. Dr. Kalnay is a distinguished university professor of atmospheric and oceanic science at the University of Maryland. Before going to the University of Maryland, she was a branch head at NASA Goddard Space Center. She later served for approximately 10 years as a director of environmental modeling with the National Weather Service, where she was instrumental in making significant improvements in the nation's numerical weather forecasting and climate models. She's an expert in predictability and ensemble forecasting, numerical weather prediction, data assimilation, coupled ocean atmosphere modeling, and climate change. She is what I call a transdisciplinary researcher, which means that she breaks down barriers in science. She is what I consider to be both a combination of a hardcore scientist and a social scientist, which makes her a very powerful mind in science. She was born in Argentina, fantastic country, famous for its delicious steaks and seafood, if you haven't been there. Beautiful country also. We're very happy, though, to have her in the US now. She received her PhD from MIT in 1971, and in fact was the first female PhD in atmospheric and oceanic science at MIT. She has many, many awards, and I won't name them all, but let me just name a few. In 2009, she received the World Meteorological Organization IMO Prize, which is an extremely prestigious international prize. She's a member of the National Academy of Engineering. She's a member of the United Nations Scientific Advisory Board on Sustainability. She's an honorable member of the American Meteorological Society. She's a fellow of the American Geophysical Union and a fellow of the American Association for the Advancement of Science, just to name a few, which is pretty amazing. Her work on the impact of land use on climate change was chosen by Discovery Magazine as one of the most important results in 2010. And her seminal paper that she wrote in 1996 and I'm going to simplify this, on the reanalysis of satellite, land, aircraft, ship, and many other data associated with climate modeling, is considered the most cited paper in her field. It's been cited over 20,000 times. And I took a look at that paper yesterday just out of curiosity, And what's really important about that paper is that not only is it the most cited paper in her field, but the number of citations has increased every single year since 1996, which means that her work is becoming more and more relevant with time, which is a sign of great science. So it's my distinct honor to welcome Dr. Kalnay, and please help me by giving her a round of applause.
Thank you very much. It was really super. Thank you. Actually, I am very, very, very happy to be at the University of Utah, and I am so delighted that I was actually asked to give 3 seminars in this visit, and it really has touched my heart. And as the dean said, Zhao Xiapu was my first student when I was still working for the National Weather Service, and I am very grateful to her that I learned as much from her as I did she did from me. So I'm going to talk about the population and climate change, and I want to check whether you can you see the thing? Or? So I wonder, are we sustainable? And so the seminar will be about sustainability under the situations that we have. So climate change, some people say it's a hoax, and actually the warmest year ever, the warmest year ever was last year, 2015, and this year is getting to be a competitor of that. So we, if you look at the series of temperature anomalies with time since 1880, you can see that there is climate change, no doubt. These are evolutions of time anomalies, temperature anomalies with time since 1850, and sea level and several greenhouse gases, CO2 and nitrous oxide and methane, and we see that they are growing. But if we look actually at a longer time series, to me it's more impressive, because if you look at 10,000 years ago and 5,000 years ago, and then the last 50 years or so, or 100 years, we can see that there were slow oscillations, and then in the last 50 or 100 years, there is a jump up that really is amazing. It's clearly out of anything that happened before. And actually, I think that we know why things sort of exploded upwards in 1950. At that time, the Haber-Bosch nitrogen fertilization method was put into practice, and people started using getting nitrogen from the atmosphere and using as a fertilizer, and since so. So since 1800, we have been using the fossil fuels that nature accumulated for many hundreds of millions of years, and nature created these fossil fuels, and we are just using it in 200 or 300 years, which is obviously what explains this jump, this tremendous jump in the amount of greenhouse gases in the atmosphere. So we are by burning the accumulated carbon, we emit CO2 and other gases into the atmosphere, and the CO2 acts like a blanket, which is the so-called greenhouse effect. So the atmosphere is clearly warming up, and the total emissions, which are what are warming the atmosphere, are the product of population times the emission per person. So we have to consider both of the emission per person and the population. So in 2009, I saw this picture for the first time, and which shows the population growth, and at that time in 2009 or 2006, the population was expected to reach a maximum of 9.1 billion at 2050, and then turn down. But actually, as we will see, it didn't happen that way. The projections are considerably higher, and it's very important to know that for the hundreds of millions of years that mankind existed, or people like us existed, the population was about 0.2, 0.3 billion in the whole globe. For a long, long time, it was almost didn't change. So it was like 200 million people. And then it took only in 1800, it reached 1 billion, and then 2 billions in 1927. And then each one of these is coming faster than the previous one. So it's expected that for the next several decades, every 11 years or so, we put 1 more billion in the Earth. So you can see here that the expectation of the 2006 United Nations projection of the population was that it would reach 9.2 billion and then start decaying. But then a few years later, in 2010, they projected this, and now the current UN projection is more than 11 billion. So we are going to increase quite a lot in just the next decades. So it's very important to know that since total emission is population times emission per person, there was a study in the London School of Economics that said that per dollar spent, the family plan 4 times as much carbon over the next 40 years as adopting low carbon technology. So it's very important to have family planning to reduce the carbon in the future. And one could think, why did the population grow so fast since the 1950s? There were basically 2 reasons. One was that people were living longer because of sanitation and antibiotics, but the most important thing was the use of fossil fuels in agriculture, which started in 1950 actually. We are using enormous amounts as fertilizers, as pesticides, irrigation, mechanization, and all of this constitutes what we call green revolution. And an example is that because of these uses, between 1950 and 1984, in these 34 years, the production of grains increased by 250%, and at the same time the population doubled. So without fossil fuels, the population would be much smaller, and the growth, unfortunately, or naturally the growth in grain production is now flattening out, and industrial farming is destroying forests, soil, and aquifers, and urban and suburban sprawl is overrunning the best farmland. So this is really not a sustainable situation. As Herman Daly, who invented ecological economics and is a very famous economist, says, we are drawing down the stock of natural capital as if it was infinite and just keep growing. And as an example, I would like to show this figure of North Korea, who used to get cheap oil from the former Soviet Union until the beginning of the 90s, when the Soviet Union collapsed, and then they had to buy it in the open market, and they got only half as much oil. And this shows the total grain produced by North Korea and the collapse that happened when they couldn't buy the same amount of cheap oil that they used before. And so I used to think that the North Korean famines were due to the horrible government that they have incompetence, but actually they managed to grow the grains until they stopped getting the cheap oil. So we should think what may happen to the rest of the countries if they don't get cheap oil. So in economics, there is actually somebody got a Nobel Prize for this model, which says that firms produce goods and services to households, and they produce labor and capital, and if you grow, the growth can go forever. So this is the standard neoclassical economic model, which does not account for inputs and like resources are outputs and stocks of natural capital, and basically it assumes that it's a perpetual motion machine that can accelerate all the time. So it doesn't include effects on the Earth system, and there are no limits to growth. And Herman Daly, who also, after he retired from the World Bank, he introduced the idea of ecological economics within the Earth system. And this is a schematic of what Herman Daly proposed. He said the human economy shouldn't be alone. It should be within the Earth system. And the human economy requires inputs like energy and matter, and those inputs require stocks of natural capital, of flows of energy, and the result of the human economy is outputs, and the outputs are basically garbage. So we have the emissions of CO2, methane, etc., the waste products, garbage, toxics, surface changes, urbanization, deforestation, desertification, etc. And all those effects go to the sinks, all these outputs, all this garbage. So the sinks are the oceans, the atmosphere, and the land. And furthermore, we have to think that the ecological this model has to have also feedback. So if we produce all this garbage and go to the sinks, that affects the human economy, and that affects the inputs, and it also affects the sources. We run out of them. So in reality, we should have the human system and the Earth system should be modeled in a coupled way with feedbacks. And this seems to be totally obvious, but surprisingly, in the most complex models that we have currently, which are the IPCC, the Intergovernmental Panel of Climate Change, are do not include the human feedbacks. So it's very surprising. So the feedbacks in an ecological model should, ecological economic model should, we think they should have included them. But many years ago, before the Industrial Revolution, the human system was really small compared to the Earth system. So the sources were large, and the impact of the human system was very small. So we could ignore the Earth system at that time when the world was empty of people, like in the 1700s. But now we are like this. Yeah, the human system is basically covering the Earth system, and the inputs are smaller and the outputs are larger, and so we call this era after the 1950 the Anthropocene. I would like to show this figure because it shows better than anything I've seen the unsustainability of what we are doing now. So we have two figures, one of the population in red, and that's the same that we saw before. And we see that it didn't grow very fast until about the beginning, the 1800 or so, and then it grows much faster, and especially after 1950. But the blue line shows the GDP per capita, and it also was quite constant, and then it grew much faster than the population. So we computed the total consumption is the product of this times this. So the product of the population times the GDP per capita. So we computed from 1950 onwards the contribution of these two factors to the total product, and it's about the red is the population, and it's about 2%, and the blue, which is more variable, is the GDP per capita. Actually, 2009 is not shown here, but it's negative, and then it became much more positive. Anyway, the consumption is growing, and it's 2% due to the population and 2% due to the GDP per capita. So the total growth is about 4% per year when you compute it. And this, if you have something that grows 4% per year, like a bank account, after 20 years you have twice as much money as you put initially. Anything that grows 4% per year will double after 20 years. So since 1950, we are doubling our total consumption of the Earth's resources every 20 years. So, and we are already consuming more than what the Earth regrows as a regrowing process, like crops or fisheries that regrow. So right now the human consumption is more than like 2 planets of regrowth. But in addition to that, we double the total consumption every 20 years. And how come we consume more than what the Earth regrows every year? It's because we are basically eating oil, are using the oil to grow, and we feel we are growing wonderfully, but it's a funny thing. One an additional important point is that there is a strong inequality in the use of, in the consumption or resource use. So this is actually doesn't show the inequality as much as many other factors, but it's how much carbon is used. That if we divide the total population into the top 10% by income, which is not much, $23 per year. So if you make $23 per year, you are in the 10% rich here. And then the 90% is less. And the consumption, the total carbon emissions are almost 50%, 50-50 for the 10% and the 90%. And then the per capita carbon footprint is therefore like almost 10 times larger for the rich than for the poor. Although rich here is not very rich. But if we look at many other statistics that I'm sure you have heard, like the Walmart owner's family makes as much money or has a wealth equivalent to, I don't know, 40% of the poor people in the United States. That's much more shocking even, but even at this low level of richness, there is like a factor of 10 in this. So I heard, I saw this figure about 2 years ago from somebody that was comparing how the models used in IPCC, the intergovernmental panel on climate change that gives us guidance on what to expect for the future. So they said in the mid-1970s, when I was a student or just finished, an atmospheric model was all that we used to estimate climate. So we just ran the atmospheric model and saw how climate, the average of weather was produced. But, and then we added land surface and ocean. And it was only after in the 90s when ocean was coupled, the ocean model was coupled with the atmosphere, that we were able to predict El Niño. This ENSO means El Niño Southern Oscillation. And El Niño is the most important climate oscillation that we have, but we couldn't reproduce anything until we coupled the atmosphere with the ocean, and that's because the El Niño is a coupled instability between the atmosphere and the ocean. So having a very good atmospheric model and trying to predict El Niño is impossible because it needs the ocean to produce effects and receive the feedbacks. And now they are very proud, and rightly so, for adding many other components like aerosol, both sulfate and non-sulfate, and carbon cycle, and all sorts of additional components of the Earth system. And they think, wow, we have such a wonderful Earth system. And when I heard this talk, I said to the speaker, I think that you are missing the most important component of the Earth system. And he probably thought I was crazy, so he said, what? And I said, the human system. And then he remained silent for a few seconds, and he said, you are right. And we have to couple the human system in order to be able to know what will happen in the future, because without coupling, it's like trying to predict El Niño without coupling, having with a very good atmospheric model and nothing, or sea surface observed temperatures at the bottom, and that's something impossible. So instead, we would like to have is a coupled Earth system, for example, represented by a global atmosphere, that atmospheric model, an Earth system model that has temperature, wind, fluxes, rain, CO2, etc., and land regions, and also the human system with also for different regions. And the human system includes the population demographics that now we are getting from the United Nations. And there are many feedbacks and arrows, but it's not a very complicated model. So I think it's perfectly feasible to do it. And actually, we have a coupled human water system for the watershed of Phoenix, Arizona, and it's giving very, very interesting results. And it's just a sub-component of this. So I think it can be done. But I think the most important thing is that this coupled system has to have policies. And the policies are very important, because if we don't have policies for sustainability, we are not going to become sustainable. We are not sustainable right now, doubling our consumption every 20 years, as if the Earth could grow, double, and sustain us forever. But with policies that are for sustainability, we can do it. And there is a map here of actually the northern part, or the middle part of South America. So this is the Pacific Ocean, the Atlantic Ocean. Here's Buenos Aires, where I was born, and this is Argentina, and here's Paraguay and Brazil and Uruguay. So why am I showing this? Because the colors show the vegetation index measured by satellite, and it tells how much forest leaves there are basically in one point. And you can see that there is a place which is a small province which is called Misiones in Argentina, and they are protecting the forest. They exploit the forest, which is their main natural resource, but they do it by government policies in a sustainable way. And you can see that the satellite knows that it's true, because they are basically saturated with forest leaves, whereas these other areas, which should also be equally red, are much worse, even in Argentina also. So one question that one can think is and people actually think it's impossible to have collapse. We are an advanced society, and it's impossible. So, but in reality, I wasn't aware until I started looking at these things. Collapses of many advanced societies have taken place in the last 5,000 years, hundreds of collapses, and very serious collapses. And for example, a recent study of the many collapses that took place in Europe during between 10,000 years ago and 4,000 years ago, when agriculture started, has found that climate forcing and war and disease are not the root cause of these collapses. So it concluded that the collapses were due to the population overrunning the carrying capacity. So in a place, in an area, there was a population, they grew, they developed agriculture, the population grew, and then it became larger than what the Earth could sustainably maintain for many years. So in order to study this, we developed a model which we called Human and Nature Dynamical Model, by shorthandy to start understanding the nonlinear feedbacks between the Earth and the human system. And I want to show now some explore the dynamics of producing historical cycles of rise and collapse. So many people think that the current trends in resource use and the growth in depletion and pollution are unsustainable. But we don't have enough studies about this, about long-term sustainability and of overshoot and collapse. So a very important factor occurs in nature, and this is shown for snowshoe hare, which are kind of rabbits, and Canadian lynx, let's call them foxes. But this is actually happening in real life, and many observations like that led to the predator and prey model. So the green are the prey, and when the predator grows, then the hares or rabbits are eaten, so the population collapses, and then the predator, which is in orange, cannot eat the rabbits because they collapsed, so the population also collapses. And this happens again and again. So this led to the predator and prey model that explains this. But would this occur in human systems? Generally, people believe that human history has been a continuous and inevitable upward trend in levels of population and prosperity. We are, since the Industrial Revolution, we are increasing the population and being more and more prosperous. But if you look at the historic